Hello, and welcome back. So, we've been talking a lot about reference frames and coordinate systems and moving back and forth between different reference frames. And this is giving us a great springboard now to start talking about the practical use of reference frames. And we do that with datums. When I first started learning about reference frames and datums, I was a little confused because I thought, why are we even using a word datum? How is that different from a reference frame, right? Whenever we go out and we collect points, we tie into some frame of reference or coordinate system. So isn't that our datum? Well, the answer is yes and no. A datum is the reference frame we're using, so an ellipsoid or a spheroid. But we need to add something in order to move to a practical use of those reference frames. So we'll talk about that. So in reference frames, we have mathematical models, right? We have the ellipsoid, and I'm going to give this a title. So far, we've been talking about purely mathematical models, right? Mathematical model is a representation of data that is sort of a best fit to a mathematical shape or set of functions, wherein we can derive exact computations, right? So that would be something like the ellipsoid, the Earth-centered, Earth-fixed system, or XYZ Cartesian coordinates. See, we have the LGH system, or let me say LBH first. So LBH, which is our latitude, longitude, and ellipsoid height. We have an LGH system, which is our easting, northing, and up. And we've been putting these ideas together so that we can represent coordinates in any one of those environments we want. But keep in mind, these are purely mathematical models. They don't represent any sort of physical geodesy, right? So let me make some room here. Now we're going to incorporate into the mathematical model, or along with the mathematical model, some physical geodesy. Now, we're going to incorporate some physical geodesy. What does that mean? So physical geodesy incorporates actual observations or measurements empirical data. So empirical data is actually the data resulting from the observations and measurements and the computations that we make from those actual measurements. Empirical data and computations from measurements. So putting those ideas together, we can very broadly define a datum as a standard reference point or points or a reference surface from which survey measurements are made. So in short, that's exactly what we've just discovered, is that a datum is all of the parameters of the mathematical models, the ellipsoid or centered Earth fixed systems, all of that information together with actual observations made in a region or across a certain area like the United States or North America. And then also, I would say, includes physical infrastructure. So physical infrastructure are how I refer to things like NGS control monuments, or benchmarks. So the physical infrastructure are those things you can actually walk to on the ground and point to and say, there's a cap or a pipe or there's something in the ground with published coordinates, and those physical infrastructure up until recently were managed and regularly checked for their accuracy, their precision, any change in the system. So all of that together is what makes a datum. So how do we use datums? Let me start with an analogy. Let's say that you have a friend, and obviously these days we just give them an address and they plug it into Google Maps or whatever to find us. But if we were to give directions, like physical step-by-step directions, think of how we do that. So we give directions by starting from and checking into physical landmarks. So I might say, can I fit that? I might say, okay, from your house, so there's a starting point. That's a physical landmark, right? That the audience and I both understand the position. That would be much like an NGS baseline or monument in the ground. So from your house, and just very rough directions, head south on I-5 for 30 miles. So that is a distance and a direction, right? You could drop the I-5, although that's helpful, and just say from your house, head south for 30 miles. So we start at a position, we give a bearing and a distance, and we're used to doing this. We do this all the time. Then we might say take exit 246. I don't know if that really exists or not, but there we have that's an actual physical landmark that we can check into on the ground. So there's that. You go to the top of the ramp, blah blah blah, etc. So we make up datums all the time, just reference points along with the directions, right? So we might then say, okay, we've arrived at the destination, go in the front door and turn right. So again, a physical check-in point and then direction. Then I could say go 20 feet, so there's a distance. And that's exactly how we use a datum, is we refer to published reference points that, well, in older systems, or even current ones, but we're moving away from we would give reference points, and then we could share our measurements with other surveyors or cartographers, engineers, and then we're all in a common reference frame, right? So we can start with the idea of the datum now in our heads. We can start specifying datums that we're used to, right? Look at as examples. So familiar datums. So datums we're familiar with are networks. That include the NGS benchmarks, and that would be for vertical datum, and control monuments, NGS control monuments, and that would be horizontal datums. As well as other published control. And I include this other published control because that's how we might think of a point on the ground in which we gather OPUS data. We gather GNSS observations, submit to OPUS, and then they quote unquote publish our coordinate by sending us a data sheet with all the information we need. And that is where we're moving to. NGS is moving more and more and more to a virtual control environment wherein they manage the satellite data, and the constellations. They publish ephemerides, and that is taking the place. That's a virtual control system that's taking the place of the use of physical monuments in the ground. So that other published control data would be just what we get from OPUS, and that's how we would tie into NAD 83, GRS 80. Okay. And so we're going to explore, essentially, there's three types of datums. So datum types. And essentially there's three, like I said. There's horizontal datums. And typically, those horizontal datums are based on an ellipsoid. Or surface model. And I want to point out that ellipsoids are Mathematical models, surface models, are empirical models. So we develop an ellipsoid from simple, pure mathematical functions, and we develop a surface model through empirical data collected out in the field, traverse points, level loops, that sort of thing. So typically based on an ellipsoid or surface model wherein, let's see, I lost my place. We can determine horizontal positions. So northing and easting, or X and Y. And these datums are horizontal datums. Are two-dimensional. System coordinates. So let's talk about one that we've heard of. Here's an example. NAD 27. That's terrible. Sometimes it's hard just to get letters down. NAD 27. So that's a horizontal datum that has been used for much of U.S. history. There's a lot of surveyors that, for whatever reason, still work in NAD 27. So NAD 27 it's a regional datum. With that region being North America. So it's intended to be a best fit to a particular region as opposed to the entire globe, the entire Earth. It's centered at Meads Ranch in Kansas. And that word centered, that is a huge call out for a difference between the NAD 27 datum and NAD 83, which we'll find out later why that's a call out. So this is centered at Meads Ranch. That means it's centered on the surface of the Earth. Okay. And then, so it's coming from that centered at Meads Ranch, that means it's a surface-based. A surface-based datum, the reason that is what used, because if you'll remember, NAD 27 is based on the Clark 1866 ellipsoid. Well, when that ellipsoid was developed, we didn't have readily available, or maybe even available at all, the computing power, the observational power, the geophysics to determine some sort of point, whether it be theoretical or empirical, that we can point to as the center of the Earth. That was just beyond the reach of practical engineering at that time. They didn't have GNSS, of course, or really viable gravitational systems to determine that where that center existed. So instead they used a point on the surface of the Earth, and through observations developed a model that closely fit the North American region. So it's not Earth-centered, Earth-fixed, it's surface-based. So that point at Meads Ranch is considered the geodetic center of the U.S. Geodetic center, or the geodetic center even of North America. And there is an actual point there. It's still being managed. It's still being, for, if nothing else, historical relevance. Let's see. So here's a gentleman, an engineer involved in placing the point. I don't know when this image was created, but he's standing with his foot on a slab of concrete, and in that concrete you can look closely. I don't know if, I can't really do much. Oop, that's not what I wanted to do. Spoiling my own my own show here. So anyway, yeah, so actual point in the ground. It's since been replaced. It was maintained, and now if you go there, you will see this plaque. It's a replica, but it's in the same position of the actual marker that is the geodetic center of North America. So, kind of cool that you can go to a ground zero for a datum that covers the entire North American continent. So yeah, Meads Ranch. Get my whiteboard back. There we go. Some more points about NAD 27. That's what we're talking about, is NAD 27. Uses Clark ellipsoid of 1866. And we've been exposed to that. We've worked with that a little bit. It uses an assumed geoid height, assumed. So now we have geoid models that give us geoid separation. We're going to talk about heights pretty soon, but let's see, assumed geoid height. And much like the reasons I gave for NAD 27 being a surface-based model, they really, for all intents and purposes, were served well by just assuming a geodetic height of that point, and then through the use of level loops, they would run and get elevations, adjust the network. So everything is based on an assumed geodetic height. Nowadays, we have good models for the geoid. It was established by terrestrial traverse level loops. Can you imagine how many level loops they had to have run, or how many level points? And triangulation. So triangulation was a big part of laying out the NAD 27 network. And then through the traverse and, or in the course of the traverse and level loops, they collected redundant measurements. Now, a lot of you have not had least squares adjustments for least squares, but we really dive into redundant measurements. It just means repeat measurements, right? Or getting measurements, observations out in the field that we could otherwise just compute. So if I have a point and then a distance and angle to two more points, that suffices to get the triangle, but I would be computing that third side, right? So measuring that third side is what gives me redundancy. And I'll just draw that out. So say we have an instrument set up here, and I'm backsighting and foresighting. And while I'm doing that, I'm going to get a distance here. And I have a distance here, and I have an angle. Well, I can actually calculate the distance here from just my observations of D1, the angle, the interior angle, and D2. That is the side angle side, which renders a unique triangle. So we can actually compute that third side. But let's say we set up and if we measure that, we collect an observation, then now our network has a redundancy of 1. We've actually measured something that we could have otherwise just calculated. So that's what redundancy is. And in the layout of NAD 27, they had a strict set of guidelines requiring them to collect so many redundant measurements within a network. So how we use the redundant measurements then is we use them in a least squares adjustment, or in the case of NAD 27, I'll say NAD 27 used a pseudo least squares adjustment. Which I will heretofore be writing LSA for least squared adjustment, so I don't have to keep writing those words out all the time. What this kind of looked like was they had all of these points in the ground. So these are actually points on mountaintops or in a desert, and they would traverse and level loop between them to get the vectors that, I'll try to draw these vectors, to get the vectors that connect them. So the distances and the interior angle. That was a terrible one. There we go. And voila, a network. Actually, apparently I ran out of memory on my computer and it just caused a technical glitch, but got rid of a bunch of files. I think I'm good. And I took the time to go ahead and draw out this network so you didn't have to watch me draw all these lines. But each of these yellow lines between the points are would be traversed distances and angles. Now, in reality, these points might be hundreds of miles apart. So obviously, in general, we're not getting these distances and angles through just one setup. There might be hundreds of setups between the points. But by the time we're done with the traverses, we have vectors between the points. And notice that we have developed measurements from each point to each other point in the network. For the most part, there might be some that are missed. Like I'm not going from the lower left-hand corner up to the southwest, far southwest corner up to the far northeast corner. But this model gives us an idea of redundancy, and I'm just doing this to kind of show you. I know a lot of you haven't taken the least squares adjustment course, but what happens in a network adjustment. So here I have just 6 points. And we have the observations. And while getting those observations, we would measure that angle and we would measure that angle. And we could just add those angles to get the full angle, but we also might observe that So that gives us some angular redundancy. And we would do that at each of the legs, right? We would get all of these angles and this angle, getting as many angular observations and distance observations as we can. And while we're here, we would get those interior angles. We might also get the entire angle, right? And we just keep going. And by the time we're done, we have all of these sets of measurements and these angles. And we would use the data we collected to perform a least squares adjustment. So we'd have a least squares adjustment, which would result in residuals. And then we would apply the residuals to get coordinates of the points from adjusted observations. And since we're getting coordinates from the observations, we're actually adjusting our network and getting publishable control then that other people can use to access the same network and perform their own surveys. Now, we might point out that oftentimes, well, anytime really in a survey, we would need to start from two known coordinates so we can calculate a bearing between them. Those are called baselines. Let's see, so let's say the end lines are our baselines. And so we'd have maybe that's a baseline. So this one's a baseline, and this one's a baseline. And the baselines, so baseline and a baseline. The baselines were measured, observed, adjusted, lots of redundancy, so they were accurate to a relative error of 1 in 1 million. So literally 1 in a million. And this is how the NAD27 network was created. It was thousands upon thousands upon thousands of points across North America that were tied together with level loops and traverses, and then the network was adjusted and had pre-established baselines that were accurate to within 1 in a million. Now remember, when NAD27 was being developed, we were still pulling chain. Probably we're using theodolites for angles. So the redundancy and the adjustment were essential to get reliable coordinates as well as the standard deviations of those coordinates. And that is, in a nutshell, the NAD27 datum. Now, when we get to the NAD83 datum, so let's jump forward in time to NAD83. And what are some points about NAD83? As we know, it's based on the GRS80 ellipsoid, just another ellipsoid definition. And unlike the NAD27, it is, the GRS 80 and NAD83 were developed to be a global fit. So remember, NAD27 was a surface-based model from empirical data and was designed to fit North America, just a portion of the globe. NAD83 is designed to best fit an entire global area. So it's a global fit. And remember how NAD27, I said, was centered at Meads Ranch in Kansas? It was a surface center, not incorporating the center of the Earth. Well, NAD83, by its development, we had technology advanced enough that we could actually start using models or creating mathematical models based on the center of gravity, center of mass of the Earth itself. So it's Earth-centered and Earth-fixed. It was developed for and using satellite positioning, or GPS at the time. Now, of course, we have GNSS, which is the incorporation of Russian, Chinese, European, and the United States satellite constellations, right? But satellite or GPS positioning. So essentially what I'm saying is that the advancement of GPS technology and satellite technology motivated and even required the development of NAD83, something more accurate to work within. Now, remember, NAD27 distances were established by pulling chains, reducing to horizontal, applying atmospheric corrections, sag corrections, all those kind of things. So a lot more margin of error there. By the development of NAD83, we're using EDM, or electronic distance measurements, which is what our total stations do now. They send out a laser and they count the difference in the shift of the amplitude on return versus on being sent out, and then calculates a distance. So electronic distance measurement, like a total station. We had more advanced, and NAD83 is based on more advanced geodetic data. NAD83 incorporated 266,000 stations. So again, we're traversing and level looping between the stations, creating a network across, whatever region, and then adjusting that network. So 266,000 stations. That's a lot of traversing. And remember, we're incorporating redundancy. So a lot of these legs between stations were run multiple times. Angles were observed at each point multiple times. So we could incorporate as much redundancy as was feasible economically, right? So 266,000 stations and 1,800,000 ish observations. Quite an undertaking. A lot of people were employed in the development of NAD83. Let's see, where are we? Points of interest. The development of NAD83 and the adjustment of the network was the largest computer problem ever solved. It's a fun little fact. Fun fact, whatever day. It was developed over 11 years. And by the time it was released and published and put out there for public use, it was practically obsolete. So practically obsolete by the time of release. Why? So it's because BC is because GPS vectors that were becoming more and more democratized. More survey firms in the private sector had access to GPS equipment and could actually perform observations and get their own GPS data and vectors. But GPS vectors were of higher accuracy and precision than the computed control positions. So it was acceptable for terrestrial work, terrestial, terrestrial surveying, but not GPS surveying. Now imagine what that means. I mean, when I try to take in the scope of a project like the development of NAD83, wherein we have 266,000 stations, so 250,000 station, 1,800,000, almost 2 million observations. How many people had to be involved in the planning of the project, the collection of the field data, the processing, the level of expertise, mathematical and technological, that would go to a project like this, and they go to release it knowing that it's already obsolete. Now surveyors can go out with GPS and collect data on a point that is more accurate than what all of that work produced. Kind of disappointing, but still good for terrestrial surveying. And in the early 80s to mid 80s, most surveyors on the ground were working with total stations and collecting distances through EDM. The terrestrial surveying, as I just stated, was able to use NAD83. But with GPS surveying, we need to incorporate more advanced low distortion projections to make it practical. So until now, I'll leave that. No, I won't. So until now, datums have been developed to incorporate mathematical models, such as the ellipsoid. But more recently, so until now, datums have been developed to incorporate mathematical models such as ellipsoids. However, now, particularly when we start getting into vertical datums, our technology is such we can start actually measuring gravity at different points on the Earth and come up with real geoid heights, right? As opposed to the NAD27 that had to use an assumed geoid height and then build everything off of that. with the technology we were getting from GPS and also other machinery and sensitivity equipment that could measure in the geophysics world, measure gravitational vectors, so we could develop an equipotential surface. So more recently, empirical data or observations such as gravitational observations and physical points so physical points in the ground, pipes and caps, what have you, or benchmarks. So I'll say like benchmarks. Or control monuments, like benchmarks or control monuments. So that is NAD 27, NAD 83, and an introduction to datums. I think I will leave it there. Next time we'll look at a few NAD 83 based reference frames that we're used to seeing, but maybe we don't really know how they're used. Okay. Anyway, just these lectures are a little more informational. We have to touch base on what a datum is before we can start working with datum conversions, which is where we're headed. All right. So email, call, text with questions, and I will see you next time.